Welcome back again. Let's continue. We're kind of finishing out our Engineering Thermodynamics Lecture series. Last couple of classes, for those of you in my class. So I normally take a couple of class periods and I talk about what is now in the 10th edition of the Chamberlain Bowles text, chapter 10 for us, chapter 9 in the older editions. And this is where we talk about both chapters 9 and 10. We focus on what we call ideal cycles. Chapter 10 and 11 now in the new 10th edition. In chapter 10, we talk about air cycles, AIR. I know my accent gets a little thick sometimes. Air cycles. Specifically, we're going to focus on the Otto cycle. That's OTTO. And then there is also the diesel cycle that we will at least discuss briefly, not very long. So if we talk about what these are, what they represent, these are what we call ideal cycles. Now, we've already seen an ideal cycle. That would be the Carnot cycle. That's probably arguably, it's the first proposed known in the literature ideal cycle we can point to. I've got a couple statements here. The Carnot cycle, because it is reversible, means that it performs better than any other cycle operating under the same conditions. And realistically, that just comes down to operating between the same two temperatures with which it's exchanging heat. Now, here's the thing. I can't point to an engine in any particular device and say, oh, that's like a Carnot engine. And we don't really have any technology that makes sense to try to operate in anything that resembles a Carnot engine. However, again, the key thing being reversible, because it's reversible, and that's the whole underlying idea, is because it's a reversible engine. It's not the fact that it's a Carnot engine that makes it the best possible version. It's the fact that it's reversible means it's the best possible version. Well, we could propose other cycles, other types of processes that are in fact reversible that would come much closer to mimicking real technology that we have that exists today, and then use that as a comparison. That's really the whole focus of chapters 10 and 11. Let's look at cycles that are ideal, that are reversible, and more closely mimic real technology, real devices that we might encounter out in the wild, so to speak. And then we can use these ideal reversible cycles to give us a ballpark idea of what the real ones could potentially operate at. Now, historically, we've employed what we call idealizations. Idealizations basically are simplifications. They're assumptions that we can make, or simplifications that we can make that allow us to model something in a fashion that's much easier to describe mathematically, perform calculations and estimations on. We acknowledge that it's only an estimation, but it's close enough, or it's within an order of magnitude or better of what a real device might actually look like. So here's an example. You can find this in our textbook. You can find it one's very similar to it in another textbook. It's a wonderful description of the difference between an idealized cycle as opposed to an actual cycle. So you see the dashed line. I assume that's some kind of a pink or maybe purple. It looks kind of pinkish red to me. I don't know what it is to you. That represents an actual cycle. So let's say we had something like an actual engine, and we plotted its pressure volume curve, and it might come out something like this. And we said, okay, well, let's say we wanted to actually find the potential work that we could extract from this process. Well, that means I need to find the area bound by this cyclic curve. And because work is the integral of pressure with respect to volume, we've been talking about that since chapter 2. That is a way you could estimate what the potential work we could extract from this process, or the work that we would have to put into the process if it's operating kind of in a compression cycle or a refrigeration cycle. If the actual cycle is the dotted line, Notice that if I were to try to find the area bound by this curve, try to perform an integral, well, I'm probably going to have to break it up because there's probably not a single function that's going to describe all of these twists and turns, nooks and crannies. Um, I could probably describe this area up here as circular, and maybe this is somewhat linear. And I've got basically kind of a circular area over here. Maybe this is some sort of a second order polynomial, and it looks like it changes right in here. So I'm gonna have to break it up, and I'm gonna have to integrate each one of these little pieces, and that's kind of where differentials, numerical analysis of differential equations comes in, as you basically break this up into a bunch of little slices and you do a bunch of Riemann sums, so to speak. Doable with modern computer technology today, still not simple. That's often kind of graduate level work for most engineers. Um, as opposed to, notice the ideal cycle, the black solid line. If I were to try to find the area bound by the black curves, all I would need to do is be able to describe this top curve right here, describe this bottom curve. This looks like probably a second order polynomial or something like that. This looks like a linear function on the bottom, or approximately linear. And then I've got vertical lines on the ends. So when I integrate those with respect to volume, those are zeros. So really all I have to do is take the area bound by the top curve, subtract from it the area bound by the bottom curve, and the difference between the two gives me a very good approximation of that area. And that's a lot easier to do than the dotted curve. And notice it gets us really close. It gets us within the order of magnitude, is what we like to say, basically within 1 to 2 significant figures. That's an example of an idealized cycle versus an actual cycle. And we make idealizations, we make assumptions to say, well, rather than worrying about this curve, let's just assume this is approximately vertical. Rather than worrying about this curve, here's a function that we can actually describe that fits in reality or within the ballpark of reality, et cetera, right? So that's what we're going to look at in chapters 10 and 11 for us. Different ways that we can idealize versions of real cycles with reversible processes, and therefore make it to where it's something we could reasonably estimate without a ton of effort and get us in the ballpark of what a performance for one of these real devices should look like. So if my working fluid is air, we call that an air cycle. There are devices that exist that air cycles make a lot of sense for. Most internal combustion engines, for what we call a spark ignition sequence, where I've got gasoline or propane, something like that, or compressed natural gas, or the diesel, which is a compression ignition process. So the diesel cycle would be another example of that. These are cycles where the working fluid, the material moving energy through the process, is air. And so if I want to treat air if I want to make air idealizations, air assumptions, these are some of the standard ones that we will use. We're going to treat the air like it's an ideal gas. Again, we acknowledge no gas is, completely ideal, but again, we're trying to estimate within an order of magnitude in a reasonably straightforward fashion. So if we treat the air as an ideal gas and we keep it in a closed loop, we'll talk more about that in a second, that makes our process of analysis much more simple. Again, these are ideal cycles. These are potentially the best case scenarios. So we're going to treat all of the processes as reversible, representing the best possible version of this particular type of device. Again, we're going to talk about models or processes that model the internal combustion engine processes. And so instead of having an air fuel mixture where I'm going to burn some of that fuel and release the energy, and now I've got how much of that air fuel mixture actually burned, what is the composition of the fuel, how much energy is stored, what's the chemistry look like, what's the stoichiometry on it. We're not going to worry about any of that. We'll leave that for a later course. Later courses can look a lot closer at how much material is combusted, how much energy per unit mass it gets released. For us, we're going to keep it straightforward. It's just heat addition. So I'm going to have a bubble of air in a closed system bubble of air. I'm going to put heat into it. And I'm going to heat the air up. And then rather than in a real engine where I've got this exhaust, the spent air fuel mixture, now I've got to yeet, if you will. I got to kick it out of the engine. I got to exhaust it out of the engine. And then so I've got area now I can replace with the brand new unspent air fuel mixture. No, no, no. We're not going to do any of that. For air idealizations, what we're going to do is, again, not going to worry about the chemistry of the combustion. We're just going to add heat in. Not going to worry about the exhaust process. Do I get all of the material out in the exhaust process? How much spent air fuel mixture gets left? Because I can never get all of it out. No, none of that. We're just going to add heat in for combustion. We're going to reject the remaining heat for the exhaust to represent the exhaust process. And that's going to get us a nice estimate for what we, at least within an order of magnitude estimate of what we would observe in a real internal combustion engine. Okay. The last thing here, I didn't realize I didn't have any more bullet points on that last slide. So I went back and here we are. The last thing on this. So I know some of my students in class, sometimes I really get on them about not just pulling specific heat properties at room temperature. That in most cases, that's wrong because we're trying to get a little more significant figures than that. Here, that actually, we go against that now. We do change that specifically for ideal cycles. We can actually just simply pull the specific heat and thermal properties of our air at room temperature as a reasonable assumption then throughout the process. Because again, we're not trying to get 4 or 5 significant figures. One or two is really probably the best we're going to do here. So at room temperature, the specific heat at room temperature is going to be to 1 or 2 significant figures the same as any other temperature on the spectrum. So it's very often, if you're working a problem for me in my class, if it's an Otto cycle, or I'm not going to ask you guys to work any diesel cycles. We're going to point to them and say, here's the differences. We will work an Otto cycle problem or two in the homework, and there will be one on the final for my class. On all of those, I am perfectly okay if you want to make this cold air assumption. There's plenty of other stuff going on with these problems, and having to guess and check to try to find a specific heat, find an average temperature specific heat, and keep track of how it varies throughout the cycle. No, it'd be enough to just pull specific heat at room temperature for these problems. Now, all the chapter 7 type problems and 8 type problems and before, no, go get a good specific heat at the average temperature. Chapter 10 problems, room temperature will be just fine. So, what does this look like? This Otto cycle, right? Now I'm going to put insulation on here, right? Because it's an old scan. I need to get a better scan of this, or go actually pull the publisher's diagrams. So I've drawn some insulation on there. So, okay, what does the Otto cycle? So the Otto cycle is the first idealized air cycle that we're going to talk about. Again, it mimics a spark ignition sequence. We're going to talk about what that means in just a second. So this is the Otto cycle process. Very similar to the assumptions we were employing, the assumptions that we just talked about a second ago. And again, that's not AUTO. It's not for automobiles. It's Otto. And I've never looked up historical information about the individual for which this is named, but it's named for an individual, last name of Otto. The Otto cycle starts out with an isentropic compression. So I've drawn insulation on here because this is isentropic. Remember, all of these processes are reversible. The second law tells us that if it's adiabatic and reversible, those two things combine to make isentropic. All these processes are already reversible. So the ones that are isentropic means there's also no heat transfer occurring. So that's the reason I've drawn the insulation. So isentropic compression means I'm going from a larger volume up to a smaller volume. With insulation in place, we minimize the heat transfer during this process to get from state 1 to 2. From state 2 to 3, we add some heat, right? So this replaces, again, the combustion process. We're not worried about the chemistry associated with, did I get a complete combustion or not? No. We're just going to add heat. We're not going to worry about the air fuel mixture, how much gets burned, any of that. Just adding heat. And then isentropic expansion. So going to a larger volume, from state 3 to 4, going up to a larger volume. Isentropic, because it's already reversible. And I'm going to insulate the system. I'm going to minimize the heat transfer. So adiabatic plus reversible means that's isentropic. So from 3 to 4, constant entropy. And then finally, again, replacing the exhaust process, we're just going to reject the remaining heat. So notice I've got work going in here from state 1 to 2. That's compression. I've got work going out during expansion. That's from 3 to 4 is work going out. I've got heat going in from 2 to 3, and I've got heat going out. Heat going out from 3 to 4. And this is what it looks like graphically. So again, isentropic compression going from a large volume to a small volume isentropically, adding heat, holding the volume constant, adding heat, that's going to increase the pressure and the temperature, and then expanding it isentropically out to state 4, to the large, back out to the larger volume, and then rejecting the remaining heat to go ahead and complete the cycle, get it back down to 1. So my 15-minute alarm went off earlier. So it's a nice stopping length for this video, and we'll start the next one. I like to break these up so they don't go too long. All right, see you on the next one.